Hi, welcome back to AP Physics C E&M Unit 13. This is topic 13.6. And so this is the last video of our journey here in the E&M portion of the class. Here we're going to talk about the last type of circuit, which is the circuits with inductors and capacitors, or what are known as LC circuits. Okay, so in circuits containing only a charged capacitor and an inductor, which we know as LC circuits, the maximum current in the inductor can be determined using conservation energy within the circuit. So LC circuits are sometimes referred, or the oscillating circuits. And so what happens is in LC circuits, the time dependence of the charge stored in the capacitor can be modeled as simple harmonic motion, right? So this oscillation piece. And so you end up with d squared dq t squared, or the second derivative of q, okay, is going to equal negative I over LC times q. Okay, now when it comes down to the end, again, the only function when taking the derivative of it twice that returns itself is a trig function. Okay, so that's why, when we say it models, so anytime you see this simple harmonic motion and it models using this second derivative differential, okay. And what happens is, because it's oscillating, it'll have an angular frequency, it'll have a period of oscillation. And so the angular frequency of oscillating LC circuit can be derived from the differential equation that's above. And you end up with omega equals 1 over root LC, okay, which actually leads us to the period equation, because omega is 2 pi over t. Okay, and if I manipulate that a little bit, I end up with 2 pi over omega is equal to the period. And remember, period is the time of oscillation. So t equals 2 pi over omega. Well, here's omega. If I substitute that in over here, I end up with 2 pi root LC. So that's the time, right? That's the period of oscillation. And what happens in an LC circuit, and you can see there's an analogy here with a mass on a spring. So capacitor charges, then it discharges through the inductor, and due to the inductor, then it will send that current back to the capacitor, charging it, and then sending it back to the inductor. So it just kind of bounces back and forth, right? So it sends the current from the conductor to the inductor to the conductor, right? Just back and forth, okay? And so that's, it's the analogy with the mass on a spring. Once you stretch that spring, it's going to go back and forth, right? Transferring essentially kinetic to potential, potential to kinetic. So it's the same thing, right? So we're going to take store some charge on the inductor or on the capacitor. Once the capacitor is fully charged, then it's going to send out the EMF or the current into the inductor. The inductor is going to do its fun work, and then it's going to pass it back. Current's going to pass through, okay, to recharge the conductor, or the capacitor, and then the capacitor is going to do the same thing, and it's just going to go back and forth over this time period, okay. So let's look at an example. So we have a 50 microfarad capacitor fully charged to 40 microcoulombs and then connected in series to a 20 millihenry inductor and an open switch. After the switch is closed, what is the maximum current through the inductor? And so what we need to do here is essentially, we need to say that the amount of energy in the conductor, or keep calling it conductor, in the capacitor is equal to the amount of energy that we stored in the inductor. And now we have equations for each one of these, right? The inductor is 1/2 Li squared. And this is what we're looking for right here, right, is I. Now we need to kind of do a little manipulating for the other equation, for the energy stored in the capacitor. So we have Q equals CV. We know that just in general, U sub C is 1/2 CV squared. And so if I want to get this in terms of Q, because notice I have, that's our capacitance. Here's our charge, right? So here's our Q, and then here's our induction or inductance. And so if I take this, what you find is that V is Q over C. And so I'm going to substitute that in. So I have 1/2 Q over C squared times C. Well, then this becomes 1/2 C Q squared over C squared. That cancels that. And so I end up with Q squared over 2C. So that's the amount of energy stored in the capacitor. So I substitute that in here. And now it just becomes algebra, right? So these twos would cancel. I end up with Q squared over C equals Li squared. Divide both sides by L. I have Q squared over LC equals I squared. And then finally take the square root of both sides to get I. So I is equal to the square root of Q squared over LC. Now do be careful because you do have the units are microfarads, microcoulombs, and millihenries, so make sure you convert those. All right, so I'm going to put in 40 times 10 to the negative 6 divided by 50 times 10 to the negative 6 times 20 times 10 to the negative 3. Okay, and the amount of current that is going to be in this in the inductor is going to be 0.04 amps or 40 milliamps. Okay. All right. So after watching all these videos, you are now set to take that AP Physics C electricity and magnetism test in May. Good luck on that, and make sure you like and subscribe.